off we go. All right, so these slides are about logic, circuits, and binary. We're back to our normal schedule of philosophy, non-programming stuff on Mondays, programming stuff on Wednesdays. We'll see how long we can keep that up. But yeah, here's the new topic, 3 different things. We probably won't get to all of them today, but we'll get a good start. I think we'll get through 2. So the first thing that I want to talk about is just logic in general, because if we want to make a good argument, we have to think logically, right? If we want to write a good computer program, we have to teach the computer what we want to do, and so we have to logically break down exactly what we want done. And so I will introduce you to the concept of formal logic. This is a very popular branch of mathematics. Everything in logic can be either true or false. So you're going to hear me say those words a whole lot today. Truth and false. What is true? What is false? What is true? What is not true? But because this is a philosophy style lecture today, let's first mess with our brains a little bit and just talk about what is truth. I think different people have different definitions. So what does it mean for something to even be true? How do we work with true and false if we don't know what true is? So let's go there first and get thoroughly confused, and then we'll come back to logic. All right? So the first stuff that I want to talk to you about is just definitions of things. You'll hear me say these a lot, so might as well put them on a slide. The word statement is going to be very, very important. So a statement is also called a proposition. These are 2 interchangeable words. A statement or a proposition, it's a sentence that could be either true or false. All right? And when I say statement, I mean a logical statement. That's what it's short for. So a statement or a proposition is just something that you could say, spit it out, that's either true or false. I don't know, today is Monday. That is a statement. It's a true statement. If I said today is Tuesday, it would be a false statement. Yeah, not too bad. What a statement or a proposition cannot be is it can't be both true or false at the same time, because that makes it not a statement. That makes it not a proposition, okay? So here's a silly example of a sentence that is not a statement, all right? If I tell you this sentence is false, it can be neither true nor false, that statement, right? If I tell you that sentence, in either case, it's not true, right? It doesn't work out. So there's a contradiction going on. So let's pretend, I'm trying to prove to you that this is not a true or false statement. So let's pretend it's true. Pretend that it's true, all right? Which means if this sentence is false, is a true statement, that means, oh no, it wasn't true, it must have been false. See how it kind of flips itself? So it couldn't have been true, because if it was true, it really meant it was false. You see that? That's a little odd. So, okay, maybe then if it wasn't true, maybe it just was false. Maybe it was a false statement, and that's how it works. But if this was a false statement, this sentence is false, if that was false, right, that means it was telling the truth about itself, right? It was telling the truth that it really was false. So in that case, it really was a true statement. So do you see how in each case, no matter what option it could have been, it really wasn't. It must have been the opposite. So that's called a contradiction. It's contradicting itself. Which means that this statement can neither be true nor false. Which means it's not even a statement. It's just a sentence that makes no sense. All right? Is that clear at all? It's a little bit of a brain teaser, but this is a sentence that is definitely not a proposition. All right? So that's unfortunate because it kind of hints at the answer to this idea. So in a perfect world, if we were all mathematically inclined, we would be able to prove that everything that is true, we'd be able to prove that it's true. We'd be able to prove everything that's false, false. We'd be able to separate things and always make sure, the true things we have a proof for and the false things we have a disproof for, okay? That is unfortunately impossible. You'll have to wait till a fancier math class to figure that out, but kind of ruins our day. But it's a nice goal. So maybe truth, to define that word, defining truth, should that just be all the things that we can prove to be true, show to be true? That could be a good definition. Right? So here are some theories of truth, because people don't agree on what it means for things to be true. All right? I'll give you these 4 today. I'm not a philosopher, so I don't fully understand them. If you've taken a philosophy class and have heard about these terms and I'm saying something wrong, please correct me. But I'm going to give you an intro to all of these things, these theories of truth, what it means to be true. Okay? The first is called correspondence theory, and this one makes sense. I think I can explain it pretty well. So correspondence theorists believe that a statement, call that statement S, they believe that S is true if and only if S corresponds to a fact. So this is kind of mathy. This is a very logical thing to say, if and only if. S corresponds to a fact, all right? So that's what they're claiming. Okay, because what is a fact? It's something that you can go out and you can see. Right? You can go be Sherlock Holmes, take your microscope, look at something, confirm that it's what it was, confirm that it's a true thing. Okay? An example will help this make sense. And then you might have to get into the definition of what a fact is, right? Because we're trying to define truth in terms of what facts are, what things are factual. And that's just another rabbit hole that I don't want to go down today. So let's pretend that we're stopping there, but you could go further. And so what they say in correspondence theory is that things that are true correspond with reality, things that you can see and touch and feel and all that stuff, okay? So, for example, snow is white. That's a statement that could be true or false, right? It's a proposition. It's a true statement. It's a true proposition because I can go and drive up to the mountains right now. Take the 168, get up to the snow, and observe that, yes, it is white. That's reality, okay? So reality and fact, they're essentially equating those terms. That's what they're thinking. Okay, so correspondence theorists define truth to be things that are facts, things that you can go out and touch and see, things that are real. Okay, so here's a silly meme about that kind of idea. Read that as I prepare for the next slide. But that's the first theory. All right, there's a bunch of different theories. People disagree. I'm not proclaiming that any of them are correct or the greatest source of truth, but I'm just giving you some options, just like I gave you options for Kantianism and utilitarianism, right? Sometimes they disagree. So the next theory of truth is called coherence theory. There's actually a couple different coherence theories, and which gets a little confusing, but I'll give you one of them. So what coherence theorists believe about truth is they say that a statement is true when it matches other true things, things that I already know are true. So I can build up little mini truths to make a bigger truth. That's what they're thinking. So here's an example of that. Like a coherence theorist does not have a hard time proving that 2 plus 2 equals 4 is a true statement because they're like, all right, yeah, I know what 2 means. I know what that symbol means. There it is a couple times. I know what the symbol 4 means. I know what the symbol plus means. And I know what the symbol equals means, right? If I put them all together, then obviously this is a true statement. It just all follows from the true stuff that I know about the smaller things, right? It follows from all that knowledge that I have about math, right? That's what coherence theorists believe true things are. I can build up bigger truths from smaller truths. Now, that's just one kind of coherence theory. It matches other true things. There's another kind of coherence theory where they believe that a statement is true when it matches the beliefs of a majority of people in society. And I think, having taken at least one history class in our time, this is a horrible idea for what is true, right? So, that's coherence theory. There's a couple different kinds. I'm not going to test you on these nitty-gritty terms. But that's the idea, yeah.
So, if coherence theory is believed on what the actual question means, isn't correspondence and coherence are the same? Because coherence theory actually states the fact that 2 equals a number, plus equals addition, and then 2 equals a number again, and then equal sign equals to like whatever the entire function means.
Yeah, so you think that coherence theory and correspondence theory are pretty much the same idea?
Pretty much the same idea.
Yeah, I think the one place where I'd say that they differ is the idea of abstraction. So 2 is an abstract concept. 0 is an abstract concept. A lot of civilizations didn't have a 0 back then, a long time ago, right? So I can't go outside and see 2. Does that make sense? You just have to understand what 2 means. And so I think that's the slight difference.
Okay. So if a majority actually believes that statement is true, that makes it a coherence theorem, and if a majority, but rather than a fact, actually proves that it is a fact, then that's a correspondence theorem. That's what you're saying?
There's actually two different kinds of coherence theory. So the one that you just mentioned was a second kind. So yeah, there's definitely gray areas here. I do think that they are quite similar, but facts versus other true things. It all has to go with how you define fact. And I don't want to go there. So you can define fact differently. It all gets a little weird. But yeah, this is a great discussion. I'm not a philosopher, so I can't really continue it much further. But if you're interested in this stuff, I encourage you all to maybe look into a philosophy class. Yeah. Any other questions before we keep on trucking? Let's see here. Yeah, so the next idea is called deflationary theory or redundancy theory. They're the two words for the same idea, same concept. And this one I really don't understand, but I'm going to tell you it anyway. Deflationary theorists think that truth doesn't exist, or it exists, but it was silly to say truth. Like, it makes no sense. It was redundant. Like, saying 2 + 2 = 4 is true. Saying that phrase makes no sense. It's silly. You shouldn't have just said is true, right? You could just say 2 + 2 = 4. You don't have to include the is true part, right? There's no need for the word truth, so there's no need to define the word truth. And so that gets a little complex, I would say. So it's not worth even trying to define this idea of truth. It's not worth having this conversation with you all right now. It makes no sense to have this section of the slides because truth doesn't exist. It's just a concept that is kind of outside what we should care about. You don't need to use the word truth ever, okay? And so this kind of gets around the whole question of what is truth. It's like, who cares? The answer is who cares? And so I am but a lowly computer scientist. I do not fully understand all the philosophical theories of truth, but this is an interesting one, I would claim, right? I think we all agree that is true. I'm just giving you a bunch of different flavors. So that's redundancy theory. Makes no sense to even define truth, right? The last one probably makes a good amount of sense, but it's a little weird. It's called pragmatic theory, all right? So here is a pragmatic theorist's view on what truth means. So they think, pragmatic theorists, they believe that a proposition is true if it is useful to believe that thing. Okay? It's like wishful thinking. So it's kind of all about utility. So John Stuart Mill would love pragmatic theory, right? Utilitarians would love it. A proposition is true if it's useful to believe. And so here's another way of saying that. Stole this from an encyclopedia. Beliefs that lead to the best payoff, that are the best justification of our actions, that promote success, those things are truths. True things, according to the pragmatists. Okay? So, it's true if it's useful to believe that it's true, right? And so, a possible pragmatic truth, now that COVID is flaring up again, perhaps, would be like, I will definitely get COVID if I go to the party this weekend, so maybe I should stay home. That's a pragmatic truth. You want it to be true, right? It's useful to believe that so that you're safe and you don't harm one of your family members, for example. But maybe if you go to the party, you'll be fine at the end of the night. Okay? It's not the same as a truth that we think about normally, right? It's not one of the other normal truths. It's a pragmatic truth. Like, it's useful to believe this, and so therefore it's true. All right? That's a little odd, but that's one way to do it. That's one way to think about it. Sometimes it's unfortunate, people who believe something so strongly that's clearly false to other people, but that just shows that those people are pragmatic theorists. That's what they think of truth. Okay? That's the idea. Any questions about any of this? I think it's a bit confusing, right? But I just want to confuse you a little bit. That was the whole point of this. Because there is no right answer, okay? There is no right answer about what even it means for something to be true. As long as you argue things well in your essays, I will take your word for it, whatever you claim that truth is. All right? So that's the idea. That's the end of my very confusing little subsection. Are we ready to go back to actual concrete math and logic now? Now that we're confused about what truth even is. All right, so let's get into the nitty-gritty of logic, symbol pushing. let's talk about Boolean algebra and truth tables, right? And the reason we have to go here, the reason we have to go to formal logic is because when you have English and you're saying words to people, I'm sure you've figured it out by now that there's plenty of contradictions and ambiguities. Like you hear one thing and you interpret it in a completely different way than the person sitting next to you would have interpreted that same phrase, right? So we need to learn to formally specify things so that there is no ambiguity, there is no contradiction. Everybody who reads it understands the same thing, all right? So that's where we're going. So English sucks. Everything is contradictory, full of ambiguities. What we'd like to do is formally specify all the propositions that we're talking about, all right? And so to get there, to motivate the topic, I have a question for you. Oh, do you have a question first?
I was actually going to say about something about
Okay.
how do you actually specify the statements, whenever you make a statement, you actually, when you finish a sentence, if the other person actually takes it in a contradictory or ambiguous terms, how do you actually like let them know that you're actually trying to say something rather than what they understood?
Yeah, maybe you have to ask them, how did you interpret what I just said?
No, they're actually returning the statement, and then they're telling you whatever they actually understood from what I actually initially stated. But whatever I initially stated was entirely different from what they understood. How would you actually specify that that was entirely different?
You mean in an argument with English?
Uh,
How would you respond in English to somebody confused? I guess you just re-explain what you were saying in a different way. Or if you both knew formal logic, you could do what we're about to do.
What if we both didn't know formal logic, and the only person that knew formal logic is the person who was trying to explain it? Because there are multiple aspects of whatever information you actually retain. It comes from different aspects. So whatever your like experiences are, you actually interpret it whatever you actually have experienced at that point in your life. And if you actually try to explain it to a different person who has never experienced whatever you have experienced, that makes it entirely like ambiguous, and it is open to interpretation in any aspect or any way that they want.
That's exactly right. And so my answer to you is there is no right answer. I don't have a surefire way to explain fully to somebody who's not understanding you. There's no right answer to that. But hopefully through the stuff that we learn in this class, you'll have some more ammunition to get your point across. Okay? Yeah. So let us have a question. Let's go to our written ice page, please, if you humor me. Please sign in for attendance. I'll stop that when I stop after we look at our answers. But let's go to the written ice page. I'll clear it out for us. Boop. And so you can write all this stuff, get together as a group, and write in what you're thinking, but I'll give you a couple minutes to respond to this. So here is how I'm going to motivate logic. Here's ambiguity in English. So let's say you go to a restaurant and you order coffee, and the waiter says cream or sugar. Okay? And then let's fast forward to, I don't know, later that night, and you're at home, and mom says you can have a cookie or ice cream for dessert. All right, so both of those sentences have the word or in them, and I'd like you to discuss as a group with the people sitting next to you the difference between those two ors, and write down as much as you can think of what the differences are. Okay? Does that make sense, the question? All right, so take a couple minutes to discuss and write down the difference between those two ors. There is a difference, isn't there? That's unfortunate. English is no fun.
How is the human sugar or substances that
Alright, that's my timer. Take a few seconds to get your answers submitted while I slowly go to that page. Well, let's take a look at what we're thinking. Alright, the difference between the two ors. Oh yeah, so the waiter is giving you a choice, right? Alright, we need to come back now. I want to make sure we leave on time. Thank you. So the waiter is giving us a choice. Yeah, very good. Thank you, Group 72. Mom is giving you a different kind of choice, right? The waiter is saying you can have either one, right? Not limiting you to a single one, but Mom is limiting us to a single option, all right? That's the idea. So is that what we got, all of us, in our discussion? I'm glad that we had a good discussion. There will be plenty of time after class to continue it, though. All right, so here is the idea. The waiter is saying you can have both if you want it, right? You can have cream, you can have just sugar, you can also you can have both if you'd like. You can have both. But Mom is saying you can't have both, right? She's giving you a choice. And sadly, in English, we use the same word for that. That's why we need to go to logic. Yes? That's where we need to be. So, let me teach you some logical symbols that will help with this, and you will never have to have ambiguity with your ors ever again. All right? So the first symbol that I want to teach you is for an operation called inclusive OR. All right? Inclusive OR. And the symbol looks like this. It's just a V. It's like a little wedge. It's like a perfect right angle almost. And what you do is you have two ideas, like cream or sugar, and you can OR them together. Cream, sugar, and this is cream or sugar. So I'll say cream ORed with sugar. Because another way of saying A or B is A or B. Okay? That is the new symbol. And so here's what it means to OR things together. Here are all the options for A, all the options for B. You can pretend that those are cream and sugar. And here's all the options of ORing them together. Do you get true or false? So this is called a truth table. This big table is called a truth table. Truth table. That thing. And it shows this new operation, A or B, under all the different possibilities for A or B. Like you're making propositions bigger propositions out of smaller propositions. So A could be true or false, right? True or false. B could be true or false. It's just showing all the different combinations, right? So if A is true and B is true, A or B is still true, right? So this is the waiter telling us you could have cream or sugar. Like we have cream and sugar. You could have both. That's totally fine. So if both are true, the answer is true. If you just wanted cream, but didn't want sugar, that's totally fine. A or B is still a true statement. And then false, true. If you just want sugar, but not cream, that's still true that you're getting cream or sugar, right? And then the only way to make it false, the OR to be false, is like if you have no cream nor any sugar. So you're not getting cream or sugar if you don't take the cream or sugar. More examples will help this make sense. But here's how I want you to interpret this symbol. It's like, I had cream or sugar in my coffee. This statement will help you understand this table. So like, if I had both cream and sugar, yes, it's true that I had cream or sugar. If I had just cream but no sugar, it's still true that I had cream or sugar. Okay? It's inclusive OR. I can have just one or the other, possibly both. And then if I didn't have the cream, but I did have sugar, it's still a true statement for me to say that I had cream or sugar. Okay, do you see how those are the three ways that it's true still? A or B? The only way for that sentence to be false is if you say I had cream or sugar, but you really didn't have cream or any sugar at all. You had neither. That was a false statement at that point, right? If you don't take either of the two. All right? So you could have one, you could have both, but you can't have neither with an or. All right? So are there any questions about that? I'll give you more symbols, and that will, in a weird way, make more sense. But that is inclusive or. All right? So you're trying to prove that something's true at the end of the day. So to prove an A or B is true, you have to show that A is true or B is true or both are true. All right? That's what the truth table is telling us. Those are the only ways that we can get truth out of A or B. And the symbol is this little V-shaped thing. All right? So that's one or. That was the waiter's or. This is a different kind of or. It's called exclusive or. That was mom's or. So people abbreviate this as XOR because they just took the X and dropped the E, I guess. And a symbol for that is a plus sign with a circle through it. So instead of saying A XOR B, you can say A plus sign with a circle in it, B. And so again, you can pretend that this is cream, and that this is sugar, and this is, it was cookie and ice cream for mom. This is a cookie, this is ice cream, and this is, I had a cookie or an ice cream. I was given the choice. Mom says you can have cookie or an ice cream. But exclusive or. All right? And so here's what that means. It's still true to take a cookie but no ice cream. It's still true that I had cookie or ice cream, right? It's still true to not take the cookie but to take the ice cream and say I had a cookie or ice cream. But exclusive or is different in that you can't have both. You see where it's different right there? You can't say that I had a cookie or ice cream and have had both when you're using exclusive or. That is where the difference lied between the waiter and the statement from mom. All right? So to prove, again, we're trying to prove something, true or false. To prove that A, X, or B is true, you have to prove that you have A or B, but not both. Like you're in one of these two statements, right? Where either A is true and B is false, or A is false and B is true. The other two cases are false. All right? And so, again, you can think of the statement as like I had cream or sugar, I had a cookie or ice cream, but it's mom's version of or now. And the way to prove something false, the way to think about false, this is the way I want you to think about it. Think about false. This will help you. Think about falsehood, something being false, as if someone was lying to you. All right? As if someone was lying. So, like, if somebody said, I had a cookie or ice cream, but they didn't have any of those, that was a lie. That was a false statement. Okay? So that's one way you can think about falseness. And so to prove A, X, or B, you have to show that you're in one of these true statements, cases. You have to show that you have A or B, but not both. Right? And that's different from inclusive or, where you can have both. All right? That's how you read those truth tables. Hopefully it's making a bit more sense. The ors are a bit confusing. The next one is a bit easier. So let's go to that one, and hopefully things will start clicking. This is called the AND combinator. So AND looks like this. This is the symbol. It's the upside down V from OR. It's kind of like the opposite of OR. So this one's easy. This is, all right, let's pretend it's cream, pretend it's sugar. And this is A and B, so you can write that as A and B, like that. And here is the statement that I want you to think about when I'm showing you this. It's the AND operation. It's like I have this and this. It's pretty logical. We have cream and sugar. This is where English actually matches logic. We have cream and sugar. Let's pretend that the waiter is telling you that. And so that was a true statement only if they really did have cream and sugar back in the back. Yeah. If they had any other possibility, right? If they really only had cream but they didn't have sugar in the back, it was a false thing to say. It was a lie to say that we have cream and sugar. Yes? See how I'm reading that? So this is the one true case when they really did have both cream and sugar for you to have. if they just ran out of cream but they still have sugar, it was still a false statement. It was still a lie to say that we have cream and sugar. Okay, see how I'm reading that? And then finally, it is definitely a lie to say that you have cream and sugar when you really don't have any of those at all. When you have neither. All right? That's A and B. That's how you combine two propositions to make a bigger one. So if you want to prove that A and B is true, you have to show like you're in this one state only. So you have to prove that both of those things were true. You have to prove that A is true and B is true at the same time. That's the one case. It's the one row of the truth table where you end up with truth at the end. Okay? So think about it as we have cream and sugar. And are you being lied to or not? Okay? That's how you can think of and. So any questions about those three? Hopefully this one is making a bit of sense because this finally matches English. Like and. We have this and this. You must have had both. That's the only way for it to be true. All right, let's keep trucking. So this one is not. Maybe it's the simplest one because it only takes one thing. So not is another word for negation. You can negate a proposition. And the symbol for it is this weird looking thing. It's like an L but mirrored and sideways. I like to think of it as like a diving board. It's like you got a person and they're about to jump off the diving board because what not does, pretend they're going to do a flip, because what not does is it flips from true to false and false to true. Right? You're negating something. Let's see here. So, let's see. Think of this in terms of the phrase, we don't have ice cream. How about we don't have cream? We're out of it. We don't have cream. So it's true when it's false, right? This is a true statement. We don't have cream. It's like saying not cream is true when the A, the original thing that you're negating, the cream, the fact that you have cream, is false, right? If you don't have it, and you say you don't have it, that was a true statement. Does that make any sense? That is not. That's negation, logical negation. So true gets flipped to false, false gets flipped to true, and the only way to make it true is for it to have originally been false. All right? That's kind of cool. So to prove that not A is true, you have to show that A was false. That's the one row of the truth table where it works out. And so this is the one combinator that takes one thing. It's like, take your A, negate it, flip it. Right? So to show that you don't have something, you just have to show that that thing was false originally. Right? We don't have cream. That's a true statement when, like this means cream, right? And we're saying not cream is true. Not cream. That's the logical version of this statement. So this is a true statement. It's a true phrase when cream really was false and they didn't have any. If they secretly had some in the back, they were lying to you, right? If that was really true, that was a false statement saying that you didn't have any. Right? So it gets a little ugly with all the symbols and it gets a little confusing, but just remember that this is the first time you've seen it, most likely, so it will grow on you. Right? One cool thing that I want to show you before I give you a question is you can actually express every possible truth table with a combination of and, or, and not. So like if you have a bunch of variables, like you got whether or not you have cream, whether or not you have sugar, whether or not you can have ice cream, whether or not you can have a cookie, blah, 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 all these variables, as many as you need, and you have some final row that you want to make sure is like under this weird combination of ice cream and cookies, it's true, under this weird combination it's false, false, true, and so some truth table with an end goal of like this, on and on and on forever. No matter what you want to get out as a combination of your original variables, you can get it out with some combination of and, or, and not. Those are powerful enough to make any truth table. That's kind of cool. And I'll kind of show that to you in a second, but that's the start of it, right? So we have inclusive or, have both or one or the other. Exclusive or, where you can only have one or the other, and where you must have both, and not, where you're flipping things. What was false becomes true. What was true becomes false. Are we good with all of those? Are we ready for a question? So I'm going to give you all these tables on Discord because it makes a bit more sense. So let me copy and paste them there, but I'll explain the question while it's opening because it will probably take a while. So I'm going to prove to you, I'm going to help you see it, that you can construct exclusive or, right? I said that you can make any truth table with a combination of and, or, not. And when I said or, I meant inclusive or. So let's make exclusive or. Let's make the truth table for exclusive or without using exclusive or. Right? Here is how it works. Exclusive or, A exclusive or B, that is equivalent to the following. Not A or B. Not A and B. Not A and B, or inclusive or A and not B. It's a bit longer, but this is equivalent to exclusive or. Exclusive oring A and B. All right? So let me prove that to you, and you will get it as an exercise. So here is or. I'll give you the ones that you need, right? Here is inclusive or. Oh, no, didn't want to do that. Come on. Okay, there's too many things going on in my computer, obviously. So here's inclusive or. Give you that on Discord if you want to go there and look at it. Inclusive or and then I'll give you not as well. And then I will close Discord because it is not happy with me. My computer is going very slow with it open. So I want you to prove that this is true, to prove that this is equivalent to this, and here's how you do it. What you do is you build a giant truth table, and I'll start out for you, and I want you to try filling it in, all right? So it's A exclusive or B, so you need some, and like stuff involving A and B, so you need to give all the options for A and B, right? Those need to be somewhere in your truth table. So here are all the options. The standard order is true, 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 false. That's a T. False, true, false, false. And then we need to build up to this, right? We need to show that its result is the same as this one's result. So, all right, to build this, we need to make not A and not B, right? So let's have little intermediate rungs of our table for those. Not A, not B. And then once we have those, we can combine them to make not A and B, right? So let's have that, not A and B. And then I also, once I have not B, I can make A and not B with that. A and not B. And then, finally, once I have that, I can make the whole thing, right? I can finally make I'll make it smaller, not A and B, or A and not B. Because I'll have both of these two things, and I can OR them together at that point using the OR operation. Yeah. And so our goal is to show that this ends up being the same row or same column as you would see with A exclusive or B. All right, they're equivalent. So let me get you started. Let me do like these three, and then I want you to try these ones. All right. So here's how you create these columns of the truth table. Under the assumptions that the variables are these, that's all you need, right? All you need to compute not A. What is not A in this row? Well, when A is true, not A is, looking up this, well, if A is true, then not A is false, right? That's how you do that. Does that make sense? So this is the statement where not A is true, where A is true, so this becomes false. Not A is false when A is true. So if A is true, not A is false. If A is false, not A is true in that row, in that column. If A is false, not A is true. Same for not B. So if I'm trying to fill this in, I have B that's true. Not B in this particular case will be false, right? So it's going to be false, true, false, true. Just flip B. That's what not B is. And now that I have this one, not A, and I still have B from the beginning, I can AND them together to get this column. All right. So what's this part? What's this part? It's not A ANDed with B, so it's going to be false ANDed with true, because that's what's happening in this row right now. So I'll go to the AND table. False ANDed with true. Oh, that's false, right? That's false if any side is false at all. So that becomes false. And then not A is false here. ANDed with B is false. They're both false. The AND of them is definitely still false. Not A and B, oh, they're both true, so the answer is true. And then not A ANDed with B, so true ANDed with false in this last case. Well, one of them is false, so the whole thing's false. All right, see how I'm filling that in using the tables? So try to fill this in and this one, And hopefully, if you get it right, you'll notice that that last column is exactly the same as exclusive OR. All right, so I'll give you a couple minutes to try that, and please ask me for help if you're struggling. I want you to get good at these. But anything, any final output you can get with just and inclusive OR and not. It's really cool. Okay. Another few seconds to try, and then I'll show you how I think about it. You'll get fast at it. I promise, with enough practice. Alright, it's okay if you're still working. Let me show you how I think about this, and you'll get quick at reading off the table eventually. You'll eventually commit it to memory. So, alright, in this case, so A and not B. So here's my A, here's my not B. True ANDed with false. Well, one of them was false, so the AND is false. Alright. True ANDed with true in this case. Okay, that one makes it true. And then, let's see, false ANDed with, well, false ANDed with anything just is immediately false. I could have stopped there, false. And then for the same reason, false. All right, so I have this row with one true in it and this row with one true in it. And now I'm ORing them together because that's the final thing. I told you that A exclusive OR B is the same as this big thing. So it's this ORed with this, inclusive OR. So let's OR these together. So this is false ORed with false. False. This is false ORed with true. Ooh, one of them was true, or both. Then the final answer with inclusive OR is true. True ORed with false. True. False ORed with false. That's the only way to make it false. Yay. So this means, what is this but the same truth table as A exclusive OR B. So you didn't actually need exclusive OR. A exclusive OR B. That was, right? False, true, true, false. They were equivalent. They're all the same. Equals, 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 equals. And so that proves that you can make exclusive OR out of ands, ors, and nots. Kind of fun. Any questions about that? How I'm using the truth table, how I read it, how I computed anything? Definitely come back and study this example. I think it's a good one. Alright, two last operations that I will not test you on. It's just very, very fun ideas. So there are two last things that people like to give names for. These operations, they're called NAND and NOR, which is kind of funny. NAND is first you do A and B. You're trying to NAND A and B together. A NAND B is the same as first do A and B, and then negate it. All right, and then NOR is the same idea. It's like A NOR B is the same as A OR with B, inclusive OR, and then negate that. And like here's the answer. Like you can compute A and B. Here's what A NAND B looks like. It's got 3 trues. Here's what A NOR B looks like. It's got 3 falses, kind of backwards. One cool thing is that I want to tell you is that NAND and NOR are called functionally complete. All right, so that's the fancy term for you can make anything out of them. So and or and not, if you use them together, any combination of and or and not can make any truth table. The fancy term for that is functionally complete. All right, so and, or, and not, you can combine those in some weird way. You can always make any truth table. That's what it means to be functionally complete. Functionally complete. And the extra cool thing, the reason that I'm giving you this slide, is that NAND by itself is functionally complete. And same for NOR, by itself. So you could just, with some weird parenthesization, get any truth table by just combining a bunch of NANDs together, a bunch of NAND operations. Isn't that crazy? Same with NOR. Both NAND and NOR are functionally complete just by themselves. You didn't need ANDs, ORs, or NOTs. You can make them from just NAND. You can make them from just NOR. And so where we're going with this is circuits. And so your computers are made of a bunch of logical circuits that are doing these Boolean operations. It makes a lot of sense to just make a bunch of NANDs at scale. It's cheaper that way, and make an entire computer processor out of that. So there's a lot of NANDs being used inside of your CPU, and it's just a bunch of NANDs. It makes everything, right? So, yeah, that's NAND and NOR. Any questions about that? I think not too bad, right? It'll make more sense once you take a fancier computer science class if you get there. All right? So, let's see. Here's my next example. I'd like to talk to you about if. We'd like to have conditions in logic. So, here's the idea. Here's, I don't know, Dad says, I'll give you $20 if you clean the bathroom and, note the parentheses, and mow the lawn or do the dishes. That whole inner part is parenthesized, all right? And so the question that you'd like to ask now is, under what conditions are you guaranteed to get $20 from Dad, okay? And so the way that we think about this is we make a truth table, all right? So I'll give you $20 if you do this. Let's call clean the bathroom A. Let's call mow the lawn B, and then do the dishes C. Right? So really what we're trying to figure out is, when can you get true always? When are you guaranteed to get true out of this logical formula, A and B or C? You see that? And that will tell us when we're going to get $20 from Dad, right? When we're guaranteed, if he's not lying to us, right? So let's make a truth table for that. So this was A, this is B, this is C, and so it's A and B or C. This part's done first. And so here's how you make a truth table for it. There are 3 variables this time, so there's 3 different combinations. So there's 3 different rows for each of those variables, and that makes 8 columns for each of those variables, and that makes 8 rows total, because here are all the different options for A, B, and C. Here's the standard way of doing it. You flip this one, true, false, true, false, true, false, true, false, and then for the next row you flip it half as often. So it goes true, true, false, false. This is just the standard order. You can put any order as long as you get them all. False, false. And this one gets flipped half as often as that. So true, 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 true. False, 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 false. Try to be aligned. And so this makes every one of the 8 possible combinations of those 3 logical variables. And so now I want to compute, when is it true when this happens? So let's compute the inner part, B or C, because then I can OR it with A. B or C. So I have these 2, true or true. That's true. True or false. That's true. And then I'll do the rest pretty quickly. True, false, true, 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 false. All right. So that's that. And then I want to AND that with A to make the last thing. A and B or with C. So now I have this. Let's AND it with A. See when it's true. So this one's true because it's true ANDed with true. True ANDed with true. True ANDed with true. True ANDed with false. Oh no, that's false. And then the rest of these are false. False ANDed with anything is false. So the rest of these are false. False, 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 false. So it seems that these are the 3 ways that I'm guaranteed to get $20 as long as Dad's not lying to me. I could be a very good child and clean the bathroom and mow the lawn and do the dishes, do all 3. Or I could be, in this case, I could have cleaned the bathroom and then mow the lawn but not do the dishes. And that's okay because I was allowed to do one or the other, right? Could have been both, though. And then finally, another way to get $20 is if I clean the bathroom, don't mow the lawn, but I do the dishes. Okay? You see how that all fills in? That is how we uphold our end of the bargain and get our $20. That's how we end up with true. Any other ones of these are where we do something wrong. So, for example, if A is false, we were required to clean the bathroom. And if we're not cleaning the bathroom, we are not getting $20. Okay? You see how I'm reading that? And so that is, I don't know, one way to apply logic to your everyday life. Any questions about this example? Because this is kind of the pattern. And oops, I don't know, I must have accidentally deleted this parenthesis. All right, are you ready? I have something for you to try. I'll give you a minute head start because it's a lot of writing. You can look up after I start it, but I want you to try it yourself. I'd like you to create a truth table for this formula, A and B, or B and not C. It's quite long, all right? So my hint to you is start it out with A, B, and C. I'll give you that much, just to make sure it's all in the same order. Let me give you the ordering of those again. It is true, false, true, false, true, false, true, false. That's just the standard ordering for your truth tables. True, true, false, false. True, true, false, false. Once we get into binary, you'll notice that it's counting down in binary. That's really what we're doing. False, 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 false. So that's A, B, and C. And so then you want the intermediate stages, right? Like if you want to do A and B, well, I have those already, so I can AND them together right here. A and B. That's this side. And then if I want B and not C, well, I need to AND together B and not C. I have B, but I don't have not C yet, so I better make that. You see how I need all those intermediate things, then I can start bringing them together. So try to fill in the rest of this and end up with this big thing on the right-hand side. All right, so I'll give you a minute head start, and then I'll start doing it too. And I'll talk while I do it, but I want you to try it. Only look up when you're getting stuck, okay? Off I go. Alright, it's okay if you're still working on it. Let's see, what was I doing here? That one, that one. It's okay if you're still working on it. But I'll continue now, and I'll fill it in. And I'll talk out what I'm doing as well. Let's see. I guess that's fine. Okay. Where are my notes? There they are. Alright, so A ended with B, so true and true. True, true, false, 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 ended with true. Well, one of them is false, so the whole thing's false, 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 false. So there's a lot of falses there. Not C, well, it's just true, false, so flip those. So false, true, false, true. False, true, false, true. And now, once I have not C, I can AND it with B, B and not C. What is that? That is, well, in this row, B is true, not C is false. If I AND them together, I get false. And for the rest, true and with true, cool. That's true, false, 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 true, false and false is false, false and true is false. So looks like there's only two truths there. And then the final answer was to OR those two together. Now I have A and B, here it is. Now I have B and not C, here it is. I want to OR them, and that's the final answer. A and B ORed with B and not C. So let's OR these two together, and so just take a true when one of the sides is true. So this one's true, true, they're both true in that one. False, I didn't really line myself up very well, but false, false, true, false, false. I believe that is the answer. And so the only way to get truth out of all this is these three cases. So when they're all true, when they're all true, when A is true and B is true, but C is false, and then when only B is true, that works too. Any questions about how I'm reading that? How I did it? Yeah.
So how did you get like for C, how did you get true, false, true, false, true, false, true, false, and then for B you got true, false, true, false?
This is just every possibility of A, B, and C being true or false. There's 8 options. You can put them in any order you want. This is just the standard order.
Okay, we can put them in any order we want.
Yeah, as long as you include them all. Like there has to be one with they're all true, one with they're all false, and everything in between.
Oh, okay.
Yeah, so those are just variables. The rest come from the variables. Okay? Yeah. All right, so once you have this, let's see, we've got about 15 minutes left. That's plenty of time. Once you have this, you can actually make beautiful drawings once you understand the operations, okay? So I'm teaching you this because it applies to computers. So I'm finally answering this question for you, all right? Because these operations are going on inside of your computer. They're all being used to do your computation. Your CPU is built out of these logical operations, and or not, NAND, nor, all those cool things, exclusive or. And you can draw little schematics for them, and I'll teach you how to draw them, all right? So these are called logic gates, all right? Here's the AND gate. It's drawn like this. It looks like the little bullet from Super Mario. And here's how you do it. It takes AND, right? It takes 2 inputs. It takes 2 things, the 2 things you want to AND together. And then there's an output wire. So these are the input wires on this side, and this is the output wire on this side. And this Q gives you back A ANDed with B, all right? That's the AND gate. This is the OR gate. It takes A and B as input. That's a bit, you remember it because it's like curvier and pointier. And then it outputs A or B. Okay? This is the NOT gate. It's also called an inverter. So these symbols are how you can make little schematics. So input is A. That's like feeding in the thing. And you can think of the negation as happening where the dot is. And then it gives you out the negation of A. All right? And so this is what's happening inside of your computer. You have little circuits that compute these answers and like feed those answers to other circuits. Right? And so what's going on is it's passing along, not true and false, of course. It's passing along electricity, yeah? So the 1, or the true, is equivalent to the number 1, which is equivalent to high voltage inside of your computer. And then the false, which is equivalent to a 0, is equivalent to the low voltage being passed around inside of your circuits, all right? So this is an AND gate, OR gate, NOT gate. This is a NAND gate. That's why I kind of mentioned that the dot is where the negation happens, because a NAND is first do the AND, then negate it. This is NOR, first do the OR, then negate it. And this is exclusive OR, so it's like the OR, but with a little extra slash there. So those are your gates, and let me show you how to build cool things with them, all right? So let's see, I'll take a little screenshot. How about that? And I'll put it both here and here. You'll need this too. There's that one. I'll eventually give that to you. And then let's just put it up here while we work. All right, so let's make a circuit for this example. Not A and B, or C and not D. Okay? And let me show you how I'll build that. I have not A. So first of all, it's taking 4 variables. So there needs to be wires for those variables, A, B, C, and D. So those are where my inputs are coming in from some other part of the computer. And now I need to do stuff with them. All right? So I need to AND together not A and B. So the very first thing I need to do is negate A. You see that? So I'll send A through this NOT gate, through this inverter. So I'll do that. That's how you draw it. And now I have running on this wire not A. All right? And I can take that with B and AND them together. So I'll bring in this wire, bring them next to each other, and then I'll draw an AND gate. B. And so running out of that now is not A and B. And I'm not the world's greatest artist, so there we go. So that is not A and B. Do you see how I'm reading that? That's how it works. It's just kind of from left to right, but it could be in any order. So then we have C and not D. So the same idea. I need not D So I can AND that with C. There's not D. Here's C. Let's bring them together. Boop, with an AND gate. Whee. And so now I have C and not D. All right, and then finally, I need to, now I have this side and this side, I have to OR them together with an OR gate. All right, so I don't know. Let me move these like this. So here's my OR gate. That's how you draw it. And then I'll bring these wires here. Boop. And so now coming out of this, we finally have our not A and B or C and not D answer. Okay? Any questions about how I did that, how I'm reading it? It's a bit easier than doing the truth tables, right? Just remember the symbols.
I have one question.
Yeah.
Are these slides up on Canvas?
Not yet. I'll post them after the lecture. All right, so with that in mind, like you make your little inputs, and then you feed them through, you try. Here's another circuit. Have your A, B, C, D. You can put them in any order you want. Maybe a different order is better. But here's your wires. Use these gates to make a circuit for this one. B or not C and not A and D. All right, I'll give you a couple minutes to try that. Make a beautiful drawing. And if you'd like to study up even more, you can take these examples and make truth tables for them. Like, when is the circuit going to output true? When is the circuit going to output false? That'll be very helpful for your first midterm. Or your only midterm, sorry. Let's see if I can make this a little bigger. Another minute to make your beautiful painting. Alright, that's my 2-minute timer. So, let's see. Let me make this small again. Let me walk you through how I might do it. So, B or not C. So that means I need to OR together B with not C. So I need to take C, whatever it was, and negate it. Right? So let's take our C wire and send it through a NOT gate. And so now I have not C coming out of that. Okay? And then I can take that with B and OR them together using an OR gate, which looks like this. Boop. So you bring in those two wires, and now coming out of this, now I have B or not C. Yeah. And so I need to do the same thing for this side, not A and D, so I can finally AND them together. So let's make not A. I could do that here, that's fine. And then I need to make D. I need to AND it with D, and so, I don't know. This is where it gets a bit ugly. But here's how you can like draw that you don't want these. Like, this kind of has to like hop over this wire, right? You have to indicate that the wires don't touch, because then like everything overheats and explodes. So here's how you indicate that your wire is hopping over the other one. It's not interacting. Boop. That's how you do it. And so this is how you bring them together. And now I can AND them. Now they're next to each other finally. Right, so that's my AND gate. And so now coming out of here, I have not A and D. Sorry, not B, but D. And now I can AND together those results, right? I have this thing, I have this thing. The final answer is them ANDed. And so here we go. Not the cleanest, but have an AND gate there. And then coming out of there is your final answer. Any questions about how I did that? Yeah.
So if we have to draw like circuits, so do we have to actually indicate that wire from A to A over B and C is actually going over it?
You don't have to. I'll still give you credit, but this is the proper way to do it at least. Any other questions? All right, so yeah, we've come very far. So we've learned a bunch of operations. Go back and study them. We've learned how to make circuits from those operations, which are going to eventually allow us to compute things. But before we get there, I want to make a pit stop in the world of binary, because that's what our computers think in terms of, right? You got your ones and zeros, trues and falses, highs and low voltages. So let me teach you binary. I'll just introduce it today, and then we'll do it next non-programming. Right, so I guess I'll be answering this question for you. Like, you understand that computers are made up of a bunch of ones and zeros. That's how they think. How does that apply to everything that we've been learning with true and false, with logic? Because this is a computer science class at the end of the day, right? So, like I said, 1 is true and 0 is false, or high voltage and low voltage. And inside of our computers, there is nothing but a ton, like billions, of logic gates. They're just super tiny, made out of transistors. And there's also a little clock signal that goes high and low. That's what you need to make a computer. That's it, all right? It's mostly logic gates, all right? That's crazy. And so this is why we learn it. It's very important. And then, yeah, just everything that we store in computers as well is encoded in ones and zeros so that we can put it inside of the processor and it can understand them, right? And, like, do stuff. So all the information that we store somewhere, like on our flash drives or on our solid-state drives, that's also just a bunch of ones and zeros. So it would do us well to learn binary so that we could understand both the inner workings of our computer processors and then also the way that information is stored for computers. All right, so that's where we're going. So I'm going to teach you binary. All right, and we will go into depth, not this time, but next time. But let me just set the scene, and we'll go from there. So binary. I would like to introduce binary by telling you the difference between binary and the numbers that we know and love as humans, right? So what we think of as humans, we work with numbers in what's called base 10. And another word for that is decimal. You've heard decimal number system, right? Decimal, that's the numbers that we know and love. We use decimal numbers, all right? And so the reason it's called decimal or base 10, like there's a Latin root there that means 10, right? So why 10? It's because we use 10 digits. 1, 2, 0, 1, 2 through 9. That's 10 digits total. See that? That's why we call it base 10, because you're using 10 digits. And the second you try to add 1 to 9, you get, like, you run out of digits and you have to add a new place. That is decimal, right? And because I'm going to introduce a new different kind of number system that looks similar, I'm going to use subscripts. So these numbers are decimal numbers. This answer is a decimal answer, 10. So I'm going to put the base at the bottom like that. I'm going to say 10 base 10. It's a decimal number that I'm indicating, okay? 123 base 10. That's how we don't, like, get confused. And the reason I do that is because binary, it's base 2, which means, immediately, once you follow this pattern, right, that the only digits you can work with in binary are 0 and 1, yeah? Which means, if you take 1 in binary and you add 1 to it, you are out of digits. You have to add a new place right then. And so that means the number 2 in binary must look like this. It must be 1, 0. All right? I'll prove that to you later. But this is why I need to use the subscript, because you'll get confused otherwise. This is the number 2 in binary. This is the number 10 in our number system in decimal. All right? Does that make sense? It's a little weird, but you'll get used to it. And so, yeah, the reason that people think that we use decimal numbers rather than some other base is that we have 10 fingers. And that's why people think that. So maybe if you lived in the Simpsons world, you would be using base 8 for everything and only going up to digit number 7. Yeah. So that's binary. Here are some last 2 words before we go. A bit is just a digit in a binary number. So somebody wanted to be cute, and so they took these 2 letters and these few letters and put them together. So like a bit is just a 0 or 1. It's a digit in a binary number. 0, 1, 1, 0, 1. So this, base 2 of course. This is a 6-bit binary number. It's made up of 6 binary digits. 6-bit number. It's kind of implied that it's binary if you say the word bit. And then a byte is any 8-bit binary number. You've heard like megabyte and stuff. This is what it means. So a byte is just any string of 8 bits. So this is some number. I'll tell you what it means next time. But this is 1 byte of information. All right? That's how you can quantify how much you're storing. All right? And then again, watch out. I'm going to use those subscripts to help us. But like the number 1010 in binary is not the same as 1010 in decimal, right? This is 1010. This one is the number 10, actually. 1010 in binary. So those are not the same number, okay? And I hope that makes sense, because you have to make places a lot sooner in binary. So this is a much smaller number than this number. All right. So I'll teach you how to convert next time, but I think that's where I want to stop. Are there any questions about this at all? That's where we'll continue with next time. So yeah, if we're good, that's all that I have for us. I'll see you in the programming lecture.